A very pleasant good morning to all and welcome to 5 days faculty development program on innovative research and development trends in electronics and communication engineering organized by Department of Electronics and Communication Engineering, GL Bajaj, Institute of Technology and Management, Greater Noida. This FDP is co-sponsored by IEEE UP section, Start in UP, a government UP initiative, IIC, that is Institution Innovation Council, and AKTU. I, Dr. Asta Sharma, on behalf of EC Department, welcomes Galaxy of Intellectuals, Your Excellency, Chief Guest of the Day, HOD Sir, Director Sir, HODs of other department, faculty members, and dear participants. Thank you for taking time out and being here today. We are very grateful to have Mr. Puneet Kumar Mishra as a chief guest of the day. The agenda for today's talk is Emerging Trends in Space Antennas, Backbone of Future IoT. Before starting that, we will give a short PPT about the department to let the speaker and the participants know about us as JL Bajar Department of EC. So just please spare time. I will be sharing my screen. So before starting with the department, I would like to briefly introduce our institute, that is GL Bajaj Institute of Technology and Management, which is one of the prestigious institution under the GL Bajaj group of institutions. It is one of Uttar Pradesh best engineering and management colleges and is known for providing its student quality education and great placement opportunities. The institute is approved by AICT, Ministry of HRD, Government of India, and is affiliated to AKTU University. The department visions to become a department of repute and prepare globally competent and socially responsible professionals with holistic knowledge and technical skills under the mentorship of Dr. Satendra Sharma, HOD, Department of Electronics and Communication Engineering. We offer BTech course, which is NBA accredited, and we as department exert best of its effort to meet objective of achieving technical excellence in the areas of electronics and communication engineering. The highlights of the department are we are witnessing increase in the number of seats from 60 seats to 180 seats. We are also providing number one rank throughout the Uttar Pradesh region. And the first year result, this is the latest that we are ranking at the top most. We are actually leading. We are having very good and dedicated faculty teams. They are actively doing research work. We have 5 research groups here who have filed 20 plus patents, and also our students are very dexterous and they have been awarded approximately 15 lakhs in the various student projects and grants. We have 11 laboratories and 6 advanced laboratories and 300 plus research articles. We as department always emphasize on 360-degree focus on student development, covering each and every elements, that is state-of-art laboratories, highly qualified faculty. We also annually organize international conference Medcom Springer, and we are getting huge participation because it is going to be held recently in October. We also organize many events like international webinars, FDPs, SSTPs, trainings, and also for students, we provide industrial visits, internships, workshops, and trainings. We also provide 100% placements and alumni interactions. And also, we invite renowned guests from IITs, NITs, government agencies, leading industry experts to our organization. We also have a department club, that is Anvita Club and Tech Bliss for students' extracurricular activities. And also we have NPTEL local chapter, ICEIT GL Bajaj student chapter, IEEE GL Bajaj student chapter, department newsletter, as well as journal. These are some of the best brains which are mentoring the bright minds, the complete faculties, and we are proud to have such a great team. These are some of the additional laboratories which are there to make our students industry ready: Cisco Networking Academy, Technology Incubation and Development Center, Center of Excellence in Biomedical, Image and Signal Processing, as well as SDR and MIMO Systems, Research and Development Lab, and CNCBS PCB routing. These are some of our glimpses of a student's achievements, where one of our student, that is Kajal Srivastav, her project was selected as amongst only 5 projects from Pan India to be showcased in front of Prime Minister Shri Narendra Modi ji and Prime Minister of Israel. Also, our students are actively participating on various platforms, where recently they have been awarded in Anveshna NCR 2021. Also, they are actively participating in many startup competitions and are bagging prizes. So, Atal Incubation Center and XG Venture, as well as Divisional Innovation Exhibition. Then we have Technovation Hackathon, where the students' project bagged first prize. Also, the students are not representing on national fronts, but are also representing on international forums, that is global platforms like Women Economic Forum, and they are not participating just like in competitions, but are actually representing as delegates. We have, as a department, signed MOU with ALTTC, BSNL Ghaziabad. Also, in current batch, that is 2021 batch, we are proud that we had record breaking placement of 92%, where the highest package was 80.2 lakhs per annum awarded by Cisco. These are the glimpses of some of our top recruiters for ECE 2021 batch. Also, our students, they are very much actively engaged in as emerging as entrepreneurs, and they are establishing their own ventures. We are focusing on the overall development of our department, not only students but faculty members and research scholars, and so we always invite renowned guests at our place, and we are very happy that we have successfully organized such events where the prominent eminents are coming and are delivering such active sessions, and we are getting a lot of praises for that. So these are some of the glimpses of the webinars which we have organized. We are providing industrial visits to the students in leading institutes like ST Microelectronics, ALTTC Ghaziabad, Electronica India, Uniconverge Technologies Private Limited, Ministry of Electronics and Information Technology. These are some of our notable alumni which are placed in reputed places, like they are serving in the Indian Army, Air Force. They are also in Airport Authority of India. They are in Department of Space, ISRO. They are also in international forums like Malaysia, Canada, and are spread all over the globe. So, and now we are proud to have them as a GLB family. So that's all for our department. If you want to reach us, you can contact us at this given email address. So this is all about us. Now I would request HOD sir to please enlighten us with your kind words.
Thank you, ma'am. Thank you very much. Respected guest of the day, Sri Puneet Kumar Mishra ji from ISRO, all HODs, Director sir, all participants, my dear faculty members and staff. Good mornings and most welcome to GL Bajaj at this platform. Thank you very much. Just talking about Puneet Kumar Mishra ji, who has joined us from such an reputed organization where we only dream that scientists of such nature, if they are delivering a half an hour talk or 1 hour talk to our organization, we can gain some another height in the field of research or some new technology what sir is going to deliver to us. Accepting invitation itself is a great honor of my department and my college. And really, sir, on behalf of my management, GL Bajaj, EC department, faculty and staff, I welcome you at this platform to say few words on recent technology without wasting any time, because I know, sir, your schedule is very busy and you have spared highly some time, because I am also from defense. So I know ISRO how much busy schedule you have. So even one of my student is also working in ISRO, sir. And so I feel blessed that at least GL Bajaj AC department is developing and always growing in such a manner that we are giving our product to build a very strong nation also. Let it be Army, Air Force, HAL, Bell, or ISRO. So your blessing is needed, and I am heartiest thankful to you, sir. And I can't say thank you very much, sir. Please take over the dash. Thank you, sir.
So,
Thank you very much. I hope I am audible.
yes, sir.
Yes,
Sir,
sir.
we will be reading your profiles. So, to introduce you before the participants, so I will request Dr. Kirti ma'am to please introduce our speaker of today.
Sure, ma'am. Good morning, one and all. Myself, Dr. Kirti, and I'm very glad to introduce the eminent speaker of today's morning session, Mr. Puneet Kumar Mishra. He has earned his MTech in the subject RF and microwave from IIT Roorkee in the year 2004. Since 2004, he is with UR Rao Satellite Center, Bangalore. He has rich experience of RF characterization of 45 satellites, 300 antennas, and randoms. He has indigenously developed C-band, Ku-band, and Ka-band compact range feeds to meet various requirements of ISRO's satellite program. He has played a pivotal role in establishing satellite level EMC facility. He is also responsible for establishment of Asia's largest subsystem level magnetic measurement facility and world's first and largest compact range with 10 meter quiet zone. He has received IETE IRSI Young Scientist Awards in the year 2012, ISRO Young Scientist Award of the year 2013, AISI ISRO Space World Gold Medal in the year 2014, GE Foundation Award for Academic Excellence and Leadership 2002 to 2004, IEEE MGA Achievement Award 2017, and 6 Best Paper Awards also. He has developed a payload to study the RF blackout phenomena during re-entry of space vehicle. He has successfully developed indigenous bus bars for high-power satellites and used in multiple spacecrafts. He has published more than 50 technical papers in international conferences and IEEE transaction papers as well. He is senior member of IEEE, fellow of IETE and IE, and life member of ASI. He is a passionate volunteer and held several leadership positions at IEEE Bangalore section and India Council as well. Presently, he is serving as Vice Chair of and Professional Activities IEEE India Council. He is also serving on global committees also as IEEE Industry Engagement, IEEE AESS, and IEEE APS. Presently, he is heading satellite antenna characterization. He is heading satellite antenna characterization test and design section of UR Satellite Center India in Indian Space Research Organization Bangalore, that is ISRO. Welcome you, sir. Welcome for just facilitating us for your kind words. Thank you, sir.
Thank you, Professor Kirti Kaushal, for your very elaborate and generous introduction. First of all, I would like to thank Dr. Astha Sharma for inviting me and being the force behind this. I know I was supposed to be here 2 days before, but because of some work-related assignment, I could not join it. But she insisted, okay, after 2 days you can come. So thank you very much. And then I also would like to thank GL Bajaj Institute of Technology, HOD, Dr. Sharma, as well as other faculty members and attendees of this faculty development program. So again, today also I'm having some paucity of time, so I will be trying to complete my presentation slightly ahead of schedule, so I hope you will excuse me. So I'm sharing my
Yes.
presentation. Let us go to the presentation.
Sure, sir.
So hope my presentation is visible.
Yes, sir.
Okay. Morning, ma'am.
Good morning.
So friends, today I will be discussing about emerging trends in space antennas, which is going to be backbone of future IoT. The outline of my presentation is first and foremost what is IoT and antenna, how they are interrelated, then
सर
how
आई
space
कार्ड कहाँ से
antenna
मिलेगा?
is related to that. Second, which is very very important, which will be we will be covering basics of antennas, then issues related to space-borne antenna system. Subsequently, I will be discussing trends and thrust areas in space antenna technologies. Then recent trends are happening in the shaped and contour beam antennas. How one can design shaped or contour beam antenna. Then multiple beam antennas as well as dual graded antenna, and I will be concluding my presentation. So once these days IoT is a very very hot topic and buzzword. Everybody wants. Everything is happening related to IoT, and huge amount of work is going on across length and breadth of technology.
Sorry to interrupt you, sir. We are receiving queries in the chat box regarding the audibility at your end. Please look into it. The voices were coming low.
Okay, now it is okay.
Participants, please let us give us your viewpoint whether you are able to hear him now.
Sir, might be a bit louder. It will be good for us, sir.
Okay, now it is okay.
Yes, sir. Yes, sir. Fine, sir.
Okay, great. So IoT continues its move into mainstream with billions of devices entering its deployment. In addition to connectivity and power, which mostly people talk about IoT, they either talk about connectivity or the power requirement. What we feel that a third area, which is antennas, needs an equal attention. Why? Because of the fundamental impact it has on device performance. Now coming to antenna, what is antenna? The antenna is the mean by which an IoT device receives and sends signal to the outside world. However, antenna decisions are often neglected until the end of the development process. Most of the time, companies or organizations, when they will deploy the IoT system, they will be focusing only on those two things: how it is connected and what is the power, because everybody wants to have less power so that longer time without any problem your sensors can work, batteries can work. So most of the impact and focus is given there. Whereas if you are neglecting the antenna related technology as well as process, what will happen? It will result in unnecessary compromise and suboptimal sighting of the antennas.
Um, Sorry to interrupt you again, sir. The participants are saying again, please check the voice at your end.
Okay, I don't know. Then it may be my microphone issues. So now I hope it is okay.
Participants, please, can you let us know whether you are able to hear now? Okay, so participants are now saying, and sir, request you to please put your slides in full screen mode also.
Yeah, I tried, but I think I'm not getting that
Okay,
option.
so no worries, sir, no worries.
I don't want to, because once I tried, then there was some issue in another
Okay,
presentation.
no worries, sir. Please continue then. No.
So I tried this to do it, but I'm not getting it. Yeah.
No worries, sir. No worries.
So in any wireless application, the choice and design of the antenna varies depending on the space available. Very, very important. I will be discussing in my subsequent applied. Even space availability is a constraint in satellites also. Then what is going to be the transmitter strength? Means how much power you can transmit and in which frequency range it is going to operate. Because ITU gives specific frequencies to each and every individual user. So we have to be very, what you can say, give lot of importance about the frequency what we are going to use. When we talk about IoT network and devices, they leverage the licensed and the unlicensed sub 6 gigahertz bands. And in that also they use very small amount of bandwidth, which is less than 5 megahertz. So once you are designing, suppose you want to design the antenna for IoT application, it is very easy to design because frequency of operation is very benign, 5 megahertz, which you can obtain very easily. But the problem comes about the radiation pattern and the transmission strength and gain. So all those problems will be there. When you talk about IoT networks, they use star, mesh, or point-to-point topologies to smartly guide uplink and downlink between gateways and end-to-end devices. You can see these are the typical topology, which is point-to-point communication or a star communication or a mesh communication. This is all networking topologies which one should use when they are discussing about IoT. Job of establishing a link is accomplished. When now we will talk about a link establishment is accomplished through the use of relatively simple omnidirectional antenna structures such as chip or PCB or whip type of antenna, rubber duck type of antenna, patch antenna, or a wire antenna. And most of the IoT based development kits which are coming now and the very famed Qualcomm's Internet of Everything development platform, or if you talk about Arduino GSM, they come with GPS, Bluetooth, and Wi-Fi and antennas inbuilt. So you can simply procure that and you can start using that. However, one should think that when everything will be based on IoT and zillions of devices will be communicating not among themselves, but with the networks across globe. When we talk about smart cities, when we talk about smart villages, because now we are talking about Internet of Everything. So when Internet of Everything is there, means whether it is a remote areas or a town or a metro or any part of the world, we want to communicate and we want to communicate remotely, then satellite based communication is the only solution where at 24 bar 7 you can communicate with anything at any location at any point of time. So with this, definitely we can say that space antenna system is going to be the backbone of IoT implementation. Why? Again, I will be emphasizing that. You may be thinking, what is the problem if I will go for terrestrial communication? So this is just data I thought that I will share with you that only 25% of the world land mass is served by the cell towers. So remaining 75% of the area, if we want to have 24 bar 7 communication, whether it is a water or whether it is a land mass or even a desert, then we should be discussing with 1 second, one phone call is there. Hello. Yeah, sorry. So I was talking that to enable massive machine to machine, which we quote unquote call M2M connectivity in remote and rural areas, coverage needs to be available beyond cell towers, and satellite based IoT deployment will be the only possible solution. And in that, wherever there is a wireless communication, you all know antennas play a very, very important role. Now, coming to the antenna parameters which one should look when we are designing any antenna. So, these are the most prominent as well as important parameters for any antenna, which is a radiation pattern, half power beamwidth, directivity, gain, antenna efficiency. And when we talk about the system level antenna performance, at subsystem or antenna alone level, antenna gain, efficiency, directivity, this is all important. But when we implement that antenna to a system, then that same gain is converted into EIRP, that is effective isotropic radiated power. And what is the input to the antenna multiplied by what is the gain of the antenna? And if you will talk about in dB term, then PT plus GT means what is the input to the antenna in dB plus what is the gain of the antenna in dB. So that becomes the parameter for the system level performance evaluation. Another very, very important thing is polarization. Polarization is important because you may be knowing that there is a scarcity of the spectrum. So throughout world, bands are limited, whether it is a L, C, X, Ku, Ka, QV, any band you go. So frequency is limited. Now that same frequency has to be allocated to all the users across globe. Then International Telecommunication Union, which is the coordinating body for this frequency allocation, how they can increase the, how can they meet the demand of the users, which is coming from several sectors. So they are implementing several of the technologies for increasing the spectrum by their own unique ways. So polarization gives a kind of a way where one can multiply the spectrum. How? Using the polarization diversity. You know, if you are using a linear polarization, then same frequency can be allocated to one user in H polarization, and same frequency can be allocated to another user in the V polarization. So using polarization diversity, we can double the spectrum in the linear polarization. Similarly, in the circular polarization, LSCP, RSCP, you give same frequency, you can double the spectrum. So this is the way how ITU tries to meet the demand of the ever increasing demand of the frequency as well as spectrum. So this is a very, very important parameter. Then now coming to axial ratio and cross polarization, this is important. This is important because when I told that same frequency is going to be allocated to the two users, whether it is in H and V or LSCP and RSCP, then this cross polarization parameter comes and plays a very important role. Why? Because you know any antenna is going to be designed and the maximum power transfer happens, radiation characteristics are optimal in the co-polarization. But by virtue of the design of the non-linearity, either of the surface of the antenna or the design of the antenna, there will be automatically cross-pole signals also coming out of the antenna. So if design is not good, what happens? Your co-pole signals will be reducing and cross-pole signals will be increasing. But this cross-pole signal will not deteriorate the performance of your antenna, but what happens? It will deteriorate the performance of the second user, which is operating at same frequency but in opposite polarization, because cross pole of your antenna, which is the orthogonal polarization with respect to your co-pole antenna, is going to be the co-pole of the second user. Suppose India is using 11 gigahertz at H polarization and Bangladesh is using 11 gigahertz at V polarization. But the cross pole of H polarized antenna, which is developed by India, will be V polarization, and this V polarization is the co-polarization of the Bangladesh. See, if my signal strength, cross pole signal strength is high, which will be acting as a co-pole for the Bangladesh, so it will go and interfere with the Bangladesh antenna, and they will be deteriorating their performance. Similarly, the cross pole of the Bangladesh antenna will be the H polarization, which will be the co-polarization for India, and it will be deteriorating the performance of the Indian antenna. So this way, if cross polarization is not taken care properly, we are going to hamper the performance of the second user, which is going to use same frequency but in opposite polarization. So that's why when ITU gives you a frequency allocation, it also gives you how much power you can transmit and how much cross pole should be below for your antenna with respect to the co-pole level. Typically, for satellite communication, it is going to be 28 to 30 dB down, which is a quite sufficient large number, and it takes state-of-the-art antenna design to have this kind of 28 to 30 dB and 33 dB kind of a cross pole values. So that shows that why this is a very important parameter. And then obviously, if you have to have antenna performance over the entire bandwidth, then your input impedance, return loss, and bandwidth should be complied over the frequency band. So that is another important parameter one should look into. This polarization of a wave already I have explained, but still I will tell you what is the IEEE definition about the polarization. The IEEE definition says that the trace of the tip of the E field vector as a function of time seen from behind. You can see this particular where instantaneous vector of the field E field is perpendicular to the earth, you can imagine, then this is a vertical polarization. This polarization definition is always with respect to a reference plane. On the ground we will take earth up, what you can say, as a reference plane. So with this, if your instantaneous vector of the E field is perpendicular to the earth, it becomes a vertical polarization, and if it is a horizontal, means parallel to the earth, it becomes a horizontal polarization. But that same definition changes when your antenna is in space mounted on the satellite. Then how that definition is given? So if instantaneous vector of the E field is perpendicular to the equator, it becomes a vertical polarization, and parallel to the equator, it becomes a horizontal polarization. So when we are giving this definition for the satellite antenna, one has to look into that aspect as well. That with respect to which frame we are defining. So that plays a very important role again. And if this definition is not taken care, even though you have designed your satellites, you cannot use the satellite in space, because that same frequencies in orthogonal polarizations are defined to some other user, and then ITU will not allow you to operate the satellite. Your entire amount is going to be wasted. So that's why uh, this parameter which we'll neglect on ground, because we know if any problem is there, we can we can rotate the antenna by 90 degree and do the necessary corrections, and we can still use the antenna. But when you are mounting the antenna on the satellite, that kind of possibility, going in space and correcting the polarization, is not at all possible. So we have to take all these precautions on ground, and we have to ensure before launch itself that everything is okay, and then only we are launching the satellite. So you can see when we talk about space antenna system, we cover the entire frequency spectrum starting from VHF to Q band. We are having helix antennas mostly used in the VHF and UHF band, and for navigation purpose we are using L and S band. For satellite telemetry, TTC commanding, we use mostly S and C band. For data link as well as data transmitter, mostly we use X band. For satellite communication, TV broadcast, and mobile telephony, 5G kind of a communication, we mostly use KU and Ka band. And now when we talk about 5G communication, Q band is picking up into the picture. So these are the entire gamut of the spectrum we will be operating, we'll be designing the antennas and putting on the satellite. The most important challenge with respect to satellite antenna is shown in this particular slide. As a satellite antenna designer, one has to see that an antenna is designed for the adequate bandwidth, for the adequate frequency range. And when you are designing your antenna, it should have immunity from the fabrication tolerances. What does it mean? It means most of the time our designers, they will design the antenna using any software module, and when you are using, you will simply give the parameters for the optimization, and you will go home and next day you come and see that your antenna is optimized and you are having a fantastic performance. What you are not giving the first or importance is the dimensions, optimized dimensions coming out of your software. It might have given excellent performance, but the dimensions what is required to realize that antenna is 11.9724, 8.6735, 2.00007, something like that. Means up to 4 decimal digits numbers are there in mm, and you are very happy that performance is good. Simply you are giving and giving, taking out that dimensions and giving it to the for fabrication. Once it reaches to the fabrication, then fabrication engineer or mechanical engineer will see that dimensions, and he or she will tell that it is not at all possible to realize these dimensions because my CNC machine or my fabrication technology does not allow this. Or suppose he or she is realizing, she will tell that within 50 micron or 25 micron I will realize, and you will tell okay, no problem, that is okay, I will go ahead with that. Once it is realized and you started testing, you are finding none of the parameters which is optimized, and when you are measuring it, it is matching with the optimized solutions. Then what you will think? What is the problem? Problem is the fabrication, because you have given unachievable targets which is not at all possible from the fabrication point of view, from mechanical realization point of view, and that mechanical engineer, they have realized within the fabrication tolerances which is typically 50 micron, but your design is so sensitive, even 10 micron deviation if it is happening, or 20 micron deviation is happening with respect to the optimized parameter, your performance is going to be haywire. What I wanted to emphasize here is being a good microwave and antenna engineer means you should be having a good knowledge of fabrication technology as well as mechanical aspect, mechanical design of the antenna. So during the optimization phase itself, you should try to optimize dimensions which are practically possible to realize. And then you should also do a sensitivity analysis of your design by changing the parameters to the worst case mechanical fabrication tolerances limit, and see that even if I am 25 micron or in some cases 50 micron away from the desired numbers, still the performance of the antenna is good. So that is called immunity from the fabrication tolerances. And this is very important aspect one should take care if you want that after fabrication also performance of the antenna is good and you are not finding any surprises in the measurement results. Low cross polarization levels, already I have defined that why low cross polarizations levels are required. Again, same thing, because same frequency is going to be given to multiple users, and you should not be interfering with the other users. So your cross polarization level should be so that even if it is reaches to the next user, it is not interfering, or there is sufficient gap is there between the your interfering signal strength versus their pole signal strength. Obviously, space is a very costly affair, so you should be choosing the fabrication technology such that one should have a low fabrication cost of the antenna. Another important aspect with respect to antenna design is, especially for the case of satellite antenna, is lightweight. Why lightweight? You may appreciate that if we are putting one additional gram on the satellite, we need 1.2 additional grams of propellant to lift that 1 gram. Means increasing of 1 gram is additional 2.2 gram of weight. And why I'm talking about grams? Because literally in space domain, we will discuss the masses in grams and we will try to optimize each and every gram of the weight so that we can have sufficient margins and we can lift the satellite without any problem, because every launch vehicle has a limited capability to lift the mass. You may be seeing India also we do few launches from our own launch pad at Sriharikota, and few launches we do from French Guiana. Why? Because our launch vehicles they are having limited capability. Like PSLV up to 2 ton only it can lift. GSLV up to 2 ton only, 4 ton only it can lift. If any satellite is beyond 4 ton, we have to go outside. We are developing our technology, but we are not capable. So you see, means the moment my satellite weight is beyond 4 ton, I have to shift over the launch vehicle. So we will try to optimize the mass such that most of our satellites they will be able to launch from the Indian mainland. So that's why lightweight. And when launch vehicle dictates the overall mass to be lifted, suppose 4 ton, out of 4 ton, most most of the weight is taken care by propellant, because I told for 1 gram 1.2 gram propellant is required. So means 2500 to 2800 grams in kilograms of weight is goes into the propellant. Then for your satellite, whatever left over is 2 ton to 2.2 ton. Suppose we are building a 4 ton satellite. In that 2000 kg overall mass of the satellite, your antenna weight will be allotted not more than 100 to 150 kg. And once 100 to 150 kg is allotted to you, in that you have to design all your antennas, whether it is a communication antenna. In addition to that, you should have TTC antennas also, and there are also TTC antennas also. There are multiple TTC antennas will be there. Communication, whether it is a multiple bands are there. So all those antennas you have to design within that the allotted budget to you, which is maximum 150 kg. So you can imagine then what will be the individual antenna weight. So you have to look that aspect as well. So you will be choosing The materials which you are going to use to build the antenna should be lightweight. The interfaces what you are going to use to attach the antenna to the satellite, they also should be lightweight, so that overall weight of your antenna system is going to be within the allocated budget. Now coming, another important constraint is, our challenge is low volume. We want to design antenna such that it is a very high end, mostly for the communication purpose, so that we can get a very high EIRP. And if we will get high EIRP, definitely our ground station pickup will be easy, and we will have sufficient margin without any disturbance, without any problem. We can pick up the signal and we can communicate with the satellite. But already I told, everything governs with the launch vehicle. The way launch vehicle has a constraint on a weight, same way launch vehicle has a constraint on a volume. I will just give an example. You can think whether you are traveling from Bangalore to Delhi or Delhi to Mathura, anywhere, you are traveling by a Maruti 800 or you are traveling by a Innova, or you are traveling with some kind of a Toyota Etios. So they all have different baggage loading capacity. So accordingly, only you can take that much luggage with you. If you are going with Maruti 800, 100, 200 liters. If it is Etios, it is more, mostly 400 liters. Innova, if you last row you are not using, then you can go up to 450 liters kind of baggage. Beyond that, anyway, you cannot take. So same way, if I'm using a GSLV or a PSLV or a Soyuz or a Proton or a SpaceX launch vehicle, so that dictates the overall volume of the satellite. Once overall volume of the satellite is defined, typically for our GSLV and PSLV, it is 3 meter by 3 meter by 3 meter. When we are having constraint of 3 meter by 3 meter by 3 meter, then I cannot have an antenna which is having a 4 meter by 4 meter by some number. It means I have to design my antenna less than that. 1 second, again one phone call is coming. Yeah, so that is the another constraint of low volume. When we are talking about multiple beam antennas, we should think about adequate beam to beam isolation. This I will be discussing in subsequent slides. And then already I told, when we are in satellites, we have to deal with multi-band, multi-polarization, multi-beams, and agility of the beam. Agility of the beam is another very important parameter. What happens when we are in geostationary orbit, then we are always pointing to one piece of a land like India. We can communicate 24/7. But mostly for the remote sensing or low Earth orbit satellite, that orbital period is not 24 hours. So that same satellite will be covering India multiple times in a day. When we are covering multiple times in a day, it means there is a limited visibility of that satellite or satellite beam to a particular ground station. Typically, it is 15 to 20 minutes. Now you think, within that 15 to 20 minutes, you have to dump all the data or all the information which you have collected during that period to that particular ground station. How you can increase this 15 to 20 minutes to say some respectable number of half an hour? By providing agility to the beam, you can increase this time of 15 to 20 minutes to half an hour. By even though satellite has moved beyond India, still you can tilt or reorient the beam towards India so that you are able to download and transmit the required information. So that's why agility of the beam is another very important aspect one should look into. Now I will be quickly going to the trends in space antenna system. We started with conventional Gaussian beam, which was having a footprint of a circle on Indian mainland. Then we moved towards shaped beam. Why shaped beam was required? If you visualize in your mind, there is an India map and you cover that India with a circle, then you can see that there are several of the portion of the beam which is going in the ocean. Where there is a water, there is a population of the human beings are very small. You don't need to communicate a TV channel to those areas where there is no man or woman residing there. It means there is a wastage of RF energy. What you can do, if you can shape the footprint of your antenna such that it is focusing only in the Indian mainland or to the islands like Andaman and Nicobar or Lakshadweep, and rest of the areas it is creating null, then your energy will be more. You are having a focused energy, and you can still communicate a better quality TV signals. So that's why we have moved towards shaped beam. Then shaped beam, when we designed, we found that there was a cross pole issues. Then we moved towards to dual graded antennas. Dual graded antennas provide typically 30 to 33 dB kind of a cross pole filtering, and we can get a very good level of cross pole levels. Then we move towards multiple beam antenna when we are talking about 5G, 6G, and beyond. With single Indian beam coverage, we cannot provide that kind of data what is required for the kind of 5G communication. Then we move to dual reflected technology and reconfigurable shape beam antennas. Reconfigurable shape beam antenna is such that you launched your satellite. One point of time you were covering India, but after few years you find that now some other user they want that Australian coverage. You can do reshaping of the antenna on board, and you can generate beams such that rather than footprint is India, that same beam is providing an Australian footprint tilted towards Australia so that you can cover the Australian territory also. So that kind of reconfiguration aspect is also possible in futuristic antennas, and we are working towards that. In the array technology, we started with array to the phased array to the active array, and then scanning of the beam, which provides agility of the beam, is already being discussed. Important electrical and physical consideration for antenna I have discussed in length. I will just discuss few points. Power handling, because we are dealing with 36,000 kilometers distance, so power requirement is very high because of the path loss going to be faced by our RF beams. And when we are in space, we are also having problem of multi-patting and RF breakdown. Then there is a consideration of electromagnetic compatibility and electromagnetic interference, because we will be operating in many bands, in many polarization at multiple power levels. So we have to see that each and every RF system is working in tandem with the overall compatibility of the satellite, and the performance of one subsystem is not getting affected because of the second subsystem. So that is called electromagnetic compatibility. Mounting and clearance, already I told, we have to see that we have designed our individual antenna, but when we are mounting it on the satellite, this mounting is having sufficient clearances, and it is also giving sufficient clearances to the sensor and from the sensors, and similarly other appendages. Size and mass I have discussed. Material requirement: when we are using any material for the space application, we have to look into the degaussing phenomena as well as degradation due to the ultraviolet particle impacts and the radiation environment. This is another very challenging aspect and a field itself, where what kind of materials can be used for a space application meeting this degaussing requirement as well as UV particle impact requirements. Next important point is body effect study. Most of the time when we are designing antennas for ground application, we will again not give sufficient thrust to this important aspect. We are thinking that as an antenna designer, my requirement is to design a very good antenna. But you can design your antenna, excellent performance antenna alone level performance will be good. But again, as a system engineer, one should think this antenna is going to be mounted on some platform. Like this antenna is going to be mounted on a satellite platform. As forget it, you design your antenna for your mobile. You might have designed your inverted F antenna or any kind of antenna for your mobile application, but that antenna is going to be mounted on a mobile platform. Now the effect of that big mobile platform on your antenna has to be studied, and the performance should be evaluated in that particular environment, in that when it is mounted on the platform. So again, very important thing, one should think that when you are designing your subsystem, you should not think about only your subsystem. You have to think that in which environment your subsystem is going to work, what is going to be mounted, and what is going to be the body effect. We have seen that typically for the low gain and medium gain antennas, this impact is very high. So once you are designing your antenna, you should have sufficient margins, design margins, so that even if impact of body is such that it is degrading the performance, but still you are meeting the situation. So that aspect one should consider. And I request each one of you who are faculty members, they should imbibe this thinking to all your students when they are designing any subsystem, or that case antennas. They should not only look the antenna alone performance or subsystem alone performance, but a system level performance, because ultimately that is only going to be your overall performance. In that scenario, you should be able to perform as per the specifications. Another important aspect is temperature limits. In space, when your antenna is there in space, the side of the antenna which is looking towards the sun will be facing temperature, or it will be feeling the temperature as high as plus 100 degrees centigrade. But the side of the antenna, the portion of the antenna which is looking towards the cold space or deep space, it will be having temperature as low as minus 100 degrees centigrade. You can think that that same antenna which is maybe having thickness of 100 mm or 200 mm, one side of the antenna is at plus 100 degrees centigrade, other side of the antenna is minus 100 degrees centigrade, and this huge transition of 200 degrees centigrade is happening within that 100 mm or 150 mm. So your antenna design, materials of the antenna should be able to withstand these extreme temperature limits. That is another very challenging aspect in the antenna design. Vibrations. When you are mounting your antenna on the satellite is mounted on the launch vehicle, and when launch vehicle is launched, means the launch vehicle is taking the satellite from ground to the intended orbit, huge amount of vibrations are being generated, and this vibration is as high as 30 to 32 G. When this kind of vibrations are being generated, Still, the joints, the connectors, the material, the surface of the antenna, they should be intact. There should not be any degradation after these severe vibrations also. So that's why when you are designing your antenna on ground itself, you have to do all those tests on your antenna, and you have to ensure that even after facing this kind of vibration, the antenna performance as well as design is intact. Grounding scheme and spacecraft charging. This will be a totally new field for you. You may be thinking why it is required. So I will tell you. When satellite is in space, it is literally immersed in the plasma. Plasma means electrons and ions. So depending upon the velocity as well as the energy of the electron, they will be continuously hitting the surface of the antenna. So some electrons will be residing. If their energy is low, velocity is less, they will hit and they will reside on the surface of the antenna. Some electrons, they will be having high energy, high velocity. They can puncture through and reside at some depth. Some of them, they will puncture through and go to the other side of the antenna. The danger comes from the electrons which are residing either on the surface or inside the dielectric or the material of the antenna. Over the time, this charge buildup will be happening. And once there is a charge buildup, there will be potential. As soon as this potential is greater than the dielectric breakdown potential of the material which you are using, there will be an electrostatic discharge. And once there is electrostatic discharge, it will simply char the material of your antenna. It will puncture the surface of your antenna. So all these kinds of problems will happen, which will be catastrophic to your antenna as well as satellite. So what we have to do? We have to solve this problem by ensuring, by designing, we have to ensure that this charge buildup is not allowed. How you can ensure this? By design, by providing leakage path to these electrons. How you can provide this leakage path or least resistance path? You have to provide at definite intervals some mesh kind of a structure, so that electrons, as soon as they are hitting the surface or residing, they are finding a least resistance path and they are grounded. They are going to the ground. So by this grounding scheme has to be designed to avoid this spacecraft charging phenomena. Your antenna has to operate in an environment which is having absence of atmosphere, which is having a hostile charge particle radiation effect, and weaker gravitational and magnetic fields. Other important points I have already discussed, so this I will skip. Now coming to the shaped beam antennas. Typical shaped beam coverages are shown in this particular slide. You can see that to cover Indian mainland, your antenna footprint should be like this. Suppose you want to cover Indian mainland as well as island, you can have a typical coverage like this. For global mainlands, you should have antenna footprint like this. For Asian coverage, you can have footprint like this. You are seeing that now you are focusing the energy of the antenna on the required or desired landmass where you want to communicate. How this is achieved? This is achieved by contour beam generation techniques. This shaped beam can be generated by three different ways. First and foremost is there is a parabolic reflector and there is a feed system which is having multiple feeds as well as a beam forming network. Then you can generate this type of a contour beam. Second is, rather than using reflector, you can simply have this direct radiating array antenna with beam forming network and you can generate. The problem with these two type of structure is the mass of the overall system is going to be very high because you are using multiple feeds. Then there is going to be a beam forming network, which is a very complicated beam forming network because you have to take care of amplitude as well as phase variation such that you can generate the contour beam. So in ISRO, we will not prefer these two technologies. We are mostly going for the third technology, which is a space shaped reflectors with a single feed system. What we are doing, we are having only one feed, but we are shaping the surface of the reflector such that it is creating the contour beams. So these three technologies are being used across space technologies to have this contour beam generation. Now you see this particular slide gives the comparison between conventional and shaped beam patterns. You can see there is a circular beam positioned with the beam center at Nagpur. If you are having such kind of a beam, you are having a very sharp beam with very high gain at near to Nagpur. But suppose you want to have same kind of a gain across India, what you can do, and this same circular beam is represented here in the red circle Gaussian beam you can see here. Now suppose you are pressing the tip of the beam such that the coverage region is increased like this black color shown in that diagram below. So when this red beam is pressed such that the same energy is going to be redistributed across India. So this is the concept is being used. So same this circular beam tip is pressed. Pressed means the surface profile is generated such that rather than focusing only at this small region, the same energy is now being uh, redistributed across Indian mainland. By this, the peak gain of your antenna is going to reduce, but the edge of coverage gain is going to be increased. It means because peak gain is only at Nagpur, but if you are having a shaped reflector, then across India you are going to have a kind of a some 52 dB EIRP kind of a thing, which initially was happening with kind of a 55 dB EIRP or 56 dB EIRP only at the Nagpur. So Nagpur level 4 dB reduction will be there, but across India you will be gaining at least 10 dB to 12 dB. So this shaping is achieved by the cost of reducing the peak gain at few locations, but increasing the gain at entire edge of coverage polygon. So this is the thing you can see. This way we are generating the conventional beam as well as shaped beams. Shaped beam generation using beam forming network, I was telling that we are not using, but mostly outside people they use. You can see that they are having this multiple feeds and a very complicated feed structure, beam forming network structure, which is a very high, what you can say, weight wise this is very high, and complication wise engineering realization wise very high. And this is the typical beam forming network. One of the satellites of Intelsat, you can see that this is the way they are generating the contour beams. This is shaped beam using direct radiating array antenna. This is mostly implemented on a microstrip patch array. You can see that amplitude variation as well as phase variation is created by scattered mounting of these patches on the microstrip patch arrays, and then their feeding techniques such that this Indian beam is generated. This is one of the technology development program we have taken it, but it is not operational things. It is just for a PDP kind of a thing, means technology demonstration purposes. But what exactly we are doing is mostly with the help of shaped reflectors. You can see reflector surface profile is generated such that it gives aperture field distribution to generate the desired shape beam using single feed. Initially, there is a simple reflector and simple feed is there. So it will have an amplitude distribution, it will have a phase distribution. Now phase distribution is tapered such that we are having a kind of a normal amplitude variation. Now for having this kind of, when this is tapered, to achieve again same kind of amplitude variation, you have to alter the reflector surface. When you are altering the reflector surface, you have achieved this and you have achieved the phase variation. But still, now second thing is you have to have this kind of a contour beam such that you are able to generate the Indian footprint. Now to achieve this, you have to further distort the surface such that you are distorting the surface, you are achieving this, and in that case, what is going to be the phase variation? So this amplitude variation as well as phase variation is generated using by appropriate distorting the reflector surface and getting the India beam. So this is the typical technology. I'm not going in detail because that itself will take one full lecture. So that is beyond the scope. So this is just to give a very, very broad side view of how it is being done. Now coming to the multiple beam antenna technology. Multiple beam antennas, the basic concept is feeds are laterally displaced to give shift in the beam. Suppose this is a black color beam you see, which is centrally mounted and it will generate one beam. But this feed is suppose shifted in either direction on the focal plane, then we can generate this blue beam as well as we can generate this red beam, depending upon which direction we are shifting the feed on the focal plane. Now, rather than shifting that feed and putting the feed at that particular location, what we can have that centrally located feed and have one more feed offset from the focal plane, from the focus in the focal plane, which can generate this blue color beam. Similarly, on the other direction, we can have one more feed shifted in the focal plane such that it can generate a red beam. It means to generate this blue, black and red beams, we need three feeds. Means what? To generate multiple beams, we need as many as feeds are required. That's why we will call it as a feed cluster is used to generate multiple beams. Multiple beam antennas are the recent trends in the communication satellite technology. Why this is being used? This is being used for efficient frequency spectrum utilization. Means what? I spoke to you in the beginning of my presentation that using polarization diversity, ITU doubles the spectrum. Now still sometimes that is not sufficient. Then what you can do? You can use spatial diversity to allocate same frequency to one portion of the land and use same frequency, same polarization to other portion of the land. Means what? Suppose same your Indian map is going to be divided in 40 different beams. You can assign 11 gigahertz to Jammu and Kashmir beam. Then don't assign to nearby, but you can assign the same frequency to your Assam beam, again same frequency to your Kanyakumari beam, and again same frequency to your Gujarat beam. It means same frequency 11 gigahertz, same polarization, H polarization, you can have now defined at Jammu Kashmir, at Assam, at Kanyakumari, as well as in Gujarat. So using this spatial diversity, you have multiplied the spectrum by 4. This is the case. This is the technology what we are using for 5G and 6G type of communication. That's why multiple beams are being generated. And once multiple beams in a very, very small focused area, there your data transmission is very, very high. and you can get a kind of a data transmission of 32 Gbps or 48 Gbps kind of a thing. So multifold reuse of frequency you are doing with this multiple beam antennas, which gives you a very high EIRP. I spoke that conventional KU beam gives you 52 dB EIRP, but when you are going for a multiple beam uh, technology in Ka band, you can get up to 67 dB kind of 15 dB enhancement is happens in the EIRP. Similarly, in the G by T to make user terminal compact, as well as it allows you to high data rate communication. You can go as high as 48 Gbps kind of a number. What are the technological challenges for this? Stringent requirement of controlling side lobes. You can see here, this blue color beam is overlapping on the black color beam. Similarly, black color beam is overlapping on blue as well as red. Red is overlapping on the black. So you have to see that you are having a stringent control on the side lobe level so that you are not interfering again with the neighboring beams. And when it is happening, then you have to control on the cross polarization to achieve high beam to beam isolation. Beam to beam isolation, you can see it is defined by these red lines. So typically for multiple beams, so beam to beam isolation is kept 16 dB because achieving beyond that is practically not possible. Then you need a very high efficient, high aperture efficient multiple feeds with wider bandwidth because same frequency spectrum is allocated to each beams. So you are having a requirement of high bandwidth, very high aperture efficiency multiple beam antennas or feeds. Then there is again need of communication tracking need, and this is specific to the satellite communication because till now you are having only one beam to cover India, and to cover India you need a beam width of minus 2.5 to plus means 5 degree kind of a beam width is sufficient. But when you are covering that same India with 40 beams, you are going to have a beam width of the order of zero point 0.6 degrees to 0.8 degrees. Means 5 degree versus 0.6 degrees. The satellite platform stability, typically what our control system provides is provides 0.2 degree, 0.2 degree, 0.4 degree. So for 5 degree being 0.2 degree kind of uncertainty is okay, but 0.6 degree beam width kind of antenna, 0.2 degree kind of uncertainty is not okay because 0.2 degree offset means 1/3 of the land mass is not covered, or you are covering some other land mass. Now, without compromising on this, how still you can use the satellite platform? Then there was a need of a tracking feed on board the satellite so that it can send a beacon signal to the ground, and then ground antenna as well as that satellite antenna, they are always tracking towards each other. So even though there is uncertainty of 0.2 degree on the satellite platform, still my antennas are looking towards each other and there is no offset in the coverage. Once you are adding a tracking feed also, then you can see the complexity of the feed cluster is very dense because you need that many waveguides. And then if you are having a transmit receive feed, then same feed will have two ports, one for transmit, one for receive. So same waveguide routings will be there. So for 40 beams, you will have 80 waveguides running on the satellite. This is just a very simple example of 5 beams. You can see there are 5 beams, and for 5 beams there are 10 waveguides routings are there because 5 for transmit and 5 for receive. This is a very even for 5 this kind of a complicated structure is there, and when we are talking about 40 beams or 32 beams, what kind of complexity will come? But yes, we are building the complexity on board so that the on ground complexity is reduced. Now, when you have designed these antennas, you have to see that you have to characterize these antennas, and for characterization, we need a very state of the art facility. In ISRO, we are having one such facility, namely compact antenna test facility. Yes. So we have characterized 45 satellites in that particular facility, more than 300 antennas, and what kind of test we are performing in that particular facility. They are typically polarization verification, pattern, pattern means radiation pattern, then beam shift, because we have to see that whether antennas are aligned properly and they are focusing on the Indian mainland only. If there is a beam shift, then rather than focusing India, they may focus towards nearby countries, which is not desired. So if any such problem is there, we have to correct it on ground, and then only we can launch the satellite. Then already I spoke about a space called body effect. Then these are the antenna level performance, polarization verification, pattern, beam shift, is called body effect. But when we are testing the satellite, we should have a system level performance. System level performance are given by following. First and foremost is EIRP. EIRP is effective isotropic radiated power, which is the figure of merit of transmit antenna. Then SFD, that is saturation flux density and gain over temperature, G by T. SFD and G by T is the figure of merit of receive antenna. So we have to see that in addition to the transmit antenna and receive antenna, what is the payload performance that comes in these parameters, SFD, G by T and EIRP. Then another important aspect is passive intermodulation product. Why it is required? Because the entire bandwidth is divided into different channels. Suppose we are allocated 250 megahertz. That 250 megahertz will be divided in 40 megahertz channels. Okay, so in each 40 megahertz, again there will be multiple divisions, because in that 40 megahertz we can transmit 3 TV channels. So those TV channels will be at different frequencies. It means in a single waveguide, there is a possibility that we will be having more than one tone signal. So if we are having, at the example I will give you, suppose if there is a two-tone channel is propagating inside a waveguide, because of the non-linearity in the waveguide joints, means suppose waveguide joints are not planar, they are one over another, or there is a leakage, or there is a rusting, or even when it is transmitted from the antenna, then because of the non-linearity of the surface of the antenna. So you know that if there is a non-linearity, because of that, if two tone signals are there, there is going to be generation of the third frequency, or harmonics generations will be there. That is called intermod products. And because it is generated because of the passive devices, they are called PIM, or passive intermodulation. And if these intermod products are generated because of active devices, they will be called as a intermod product. Whereas if it is generated because of the passive devices, they will be called as a PIM. So this is another important things which, as a system or a satellite level, we have to look into that, which is not given a due consideration or due um, what I can say weightage when we are talking about antenna level performance. But at the system level, we have to give the consideration. We will be doing those tests also. Then another test is auto compatibility. Auto compatibility means satellite, as if satellite is in the space and each and every subsystem is on, then we have to see the compatibility between the payload system to the TTC systems, TTC system to the payload system to the mainframe system to the TTC system. So all those compatibilities has to be checked into. Then what is the need of this test is in satellite application, it is desirable to characterize the subsystem level performance and then integrated spacecraft level. There are three important aspects why we need to perform this test again at integrated level in satellite. There are these 3 points: to verify the mounting of all the antennas on the spacecraft, to verify the spacecraft body induces no disturbance on the previously measured radiation pattern, to ensure that there is no degrading impact on the spacecraft performance from environmental test. The second point, spacecraft body effect, I have dealt in detail. I will be discussing only first and third point. I have written that to verify the mounting of all the antennas on the spacecraft. Why this is required? This is required once you launch the satellite and satellite is in geostationary orbit. That particular point of time, satellite will be always looking towards the equator. When satellite is looking towards equator, because antennas are mounted on the satellite, antennas also will be looking towards equator. But this is not desirable because your antenna should look towards India, then only you can communicate. And you know, from equator to Indian mainland, there is a 22 degrees of bias is there. Typically, the Indian beam center is 83 degree east and 22 degrees north. North means 22 degree north means from equator it is 22 degrees up, which is the beam location of the Nagpur, which is the India beam center. So this 22 degrees of offset, how we are taking care? This 22 degrees of offset from the equator is taken care by providing mechanical offset on every antenna. So that even though satellite is looking towards equator, my antenna is looking towards India. We have given this mechanical offset, but how to verify that whether it is pakka or not? To verify that the given mechanical offset is proper and the beam formation is really happening on India, we have to perform a RF radiation test. And that time, after doing the test, when you plot this on a globe, automatically this pattern should go and sit on the India. Then it is proper. So that kind of a test we are performing in this facility. Third thing, I already told that in space there is going to be a huge temperature variation. Then there is going to be a vacuum. So in vacuum, in those temperature variations, we have to see the performance of the antenna as well as satellite. So we will be taking the satellite to a thermo vacuum chamber where we are creating a vacuum as well as those temperature variations, and then we are testing and seeing that my satellite as well as my antenna is performing well. Then second test is vibration test. We will be taking the satellite as well as antenna on a vibration shaker and we will be creating launch vehicle vibrations, and we have to see that my satellite as well as antenna is performing well. Then during launch, there will be huge amount of sound is created. Just to give you an example, when we are launching a satellite from a launch pad, nearby 3 kilometer area is cordoned off. Nobody, no living things are allowed. If any living thing is allowed within 3 kilometer area, they will not be alive. Even the control center, what you are seeing on your TV channels, they will be minimum 3 to 5 kilometers away from the launch site. It means there is a huge amount of acoustic load is created that we have to simulate in a chamber. We are creating those things in acoustic test facility and then seeing that my satellite as well as antenna is performing nominally. So all these tests we are performing on the satellite, and then we are bringing the satellite to our facility. That is going to be the last test before the shipment to the launch site. After these severe environmental tests, we have to ensure that neither the antenna nor the payload performance is degraded. So these are the three major objectives of doing the test at integrated satellite level in this particular facility. Then what is the need of the state-of-the-art facility what I was talking about? You can see that in the past we were having antennas which was having a Gaussian beams, which I spoke already, having a circular footprint on the Indian mainland. Then present is we are having a shaped beam which is covering the India, and future is that entire India is going to be covered by multiple beams. And these beams are becoming narrower and narrower to gain again higher data rate. This aforementioned antennas testing requires a facility which can create an excellent quality plane wave, which should have very low cross pole level, because I am talking about we have to design an antenna which gives a cross pole of 28 to 30 dB. Now, once we have to measure that 30 dB of cross pole, we cannot measure that 30 dB cross pole in a facility where facility cross pole itself is 20 dB. It means we should have a facility which should have at least 6 dB better than the measured antenna. So means we should have a facility which can give a kind of inherent cross pole of 36 dB minimum. Then when we have to measure these small beams of 0.6 degree beam width, we should have a highly accurate positioning system. And because we are simulating space, we have to have sensitive receiver, because we are going to have an enormous amount of path loss happening. Then we have to create a space condition in the facility. How space is being created in the facility? First and foremost is we have to create a microgravity. Then we have to create a rear far field condition, and then we should have a facility to map the footprint on the earth. Whatever measurement we have done, we should be able to map it on our earth. We are able to create the rear far field condition in our facility, which collimates the spherical wave into excellent quality plane wave. But this plane wave is not going to be created in the entire facility, but it is created in a small volume of 5.5 meter by 5 meter by 8 meter. And this is called quiet zone. And this is generated with the help of this double reflector geometry. You can see there are a huge reflector. This is called sub reflector, main reflector, and here source is there. From here, RF source, it goes to the sub reflector, then main reflector, then here. 1 second, again, one phone is there. Yeah. Sorry, now I have to quickly complete because I have to go somewhere. So this is the thing we are creating in 5.5 meter by 5 meter by 8 meter with this facility. And facility, you can see that we are creating an amplitude taper of less than 1 dB, phase taper 5 degrees. Typically for far field condition, phase taper is 22.5 degrees, but in our facility, we are creating only 5-degree phase taper. It means we are creating a 8 dB square by lambda condition, then cross polarization is 38. I was talking about minimum 36 is required, but we are having 38 dB. Shielding effectiveness is 80 dB, and frequency band is 1 to 200 gigahertz. Presently, we are using up to 40 gigahertz. The special accuracy requirement is our angular precision is 0.01. Heavy duty position up to 6-ton class of satellite we can test, and receiver sensitivity is minus 110 dB. And this is the 0G when we are creating. You can see these are the deployable reflector. We know the mass of the reflector. We know what is the CT line passing through that. And 12th standard physics, R equals to mg. You apply a thrust force on this reflector antenna. We can create a microgravity in here. Then we are doing a radiation pattern through this raster scans. You can see minus 5 to plus 5 degree in the steps of 0.1 degree, and elevation minus 3.5 to 3.5 in the 0.2 degree step. If we can do raster scan, we can generate a 3D pattern, and we can create a we can find out what is the performance. So this is the typical dotted versus solid line. Dotted is subsystem level performance. Solid is a satellite level performance. You can see that for high gain antennas, co-pole, there is not much variation, but at the cross pole level, there is a lot of variation there. So that's what I was telling. There is an impact on the cross pole, on the medium gain as well as low gain antenna, because of the space cloud body effect. And same thing we have tested actually when satellite was in the geostationary orbit, and you can see there is excellent match. It means whatever quality of plane wave we are generating, we are able to match in the space also. this will take time. I will not discuss much on that. And with this, I will complete my presentation. Thank you very much. Sorry, I have to go again another meeting. And if you are having any questions, I can take one or two questions. Dr. Astha, please consolidate those questions. Mail me. I will
Yes, sir,
ensure
sure.
that I am answering all the questions.
Definitely, sir. Definitely. We have one interesting question here in the chat box as well. Uh, why most of time we calculate power rather than energy calculation in RF and microwave domain? Is that any measurement constraint with energy measurement?
सर आपकी माइक बंद है.
Sir, you're muted.
Okay. Now, hope I am audible. Yeah.
Yes, yes.
So in microwave domain, what happens? We are measuring power rather than energy because when we are designing the antenna, it is having some bandwidth. Okay, so once bandwidth, so our signals are band limited signals, suppose. So when we are having this, so you will be utilizing mostly power meter in the frequency domain. And so whatever energy is being received is in the form of power rather than directly energy. We cannot measure it because individual frequencies we have to measure and find out how much is the power level it is reaching. So this is the reason why we are doing the power measurement rather than energy measurement.
Sir, I am disturbing just one.
Yeah, please, Dr. Sharma, please go ahead.
Actually, my doubt is how grounding in space for a spacecraft is achieved.
Very good question, sir. Very good question. So what is happening? You know on ground also how ground is created. If you terminate the plus and minus signal to, then you can create a ground.
Yes, sir.
So there in space, the entire satellite body is terminated and that is acting as a ground. Okay. Whatever spacecraft structure is there, whether we are mounting a battery or whether we are mounting any DC-DC converter, all things are mounted on the spacecraft structure, and then spacecraft structure is acting as a ground. So that is called a ground on the space.
Okay. So normally what communications, all PCBs and all, it is grounded with the body of the spacecraft?
Yes.
Thank you, sir. Thank you very much.
Yes, sir. I am reaching, sir. 2 minutes. No, sir. I am coming. So, Dr. Astha,
yes, sir, definitely. We do understand your busy
schedule. Thank you very much. Any questions?
Thanks a lot, sir. Thanks a lot. I'm very much thankful to you, sir. I know your busy schedule. Thanks a lot, sir. Thank you, sir.
Okay, so because our speaker, he had a busy meeting right now. So thank you all for joining us today's session, and the attendance link will be shared in afternoon session. So please do attend those both the sessions. Okay, and thank you all. Let's meet at 2:30.
Namaste, ma'am.
Okay, so I'm ending the meeting here. Thank you.
मैम सेकंड सेशन कितना बजे से है?